Hello everyone, welcome back to Must Electronics. In the previous episode, we successfully ran Android on Raspberry Pi. We explored the Android system using ADB commands. We saw important processes like Zygote and SystemServer running. But here is the important question. When we talk about Android architecture with its different layers, where exactly does all of this exist in the actual source code? Today, we are going to do something different. We are not just going to learn Android architecture theory. We are going to open the real AOSP source code and map each architectural layer directly to its location in the codebase. By the end of this video, you will know exactly where every major Android component lives, and you will be able to navigate the Android source code like a professional Android platform developer. Let me first show you the Android open source project, commonly known as AOSP. AOSP is the complete source code of the Android operating system. This is the same source code that Google uses to build Android, and it is the same source code that phone manufacturers like Samsung, Xiaomi, and OnePlus use to build Android for their devices. When you first look at the AOSP directory, you will see many folders. This can be overwhelming at first, but do not worry. We will understand the most important directories today. Let me list the key directories that we need to know. The frameworks directory contains the Android application framework. This is where Android APIs and services are implemented. The system directory contains low level system components and native utilities. The packages directory contains the Android applications like settings, launcher, and dialer. The hardware directory contains the hardware abstraction layer or HAL. The kernel directory contains the Linux kernel source code. The device directory contains device specific configurations for different Android devices. These six directories form the backbone of Android. Let's now map the Android architecture layers to these directories. Before we dive into the source code, let me quickly explain the Android architecture. Android is not a single monolithic system. Instead, it is structured in multiple layers like a stack. At the very top, we have the applications layer. This includes all the apps that users interact with, like the settings app, phone app, and camera app. Below that, we have the application framework layer. This layer provides APIs that app developers use to build applications. It includes managers like Activity Manager, Package Manager, and Window Manager. Below the framework, we have the native libraries layer. These are C and C++ libraries that provide low-level functionality like graphics rendering, database management, and media playback. Below the native libraries is the hardware abstraction layer or HAL. The HAL acts as a bridge between Android framework and device hardware. This is what allows Android to work on different types of hardware. At the very bottom is the Linux kernel. The kernel manages hardware resources, process management, memory management, and security. Now I'm going to open the actual source code and show you where each layer exists. Let's start with the top layer, which is the applications layer. All Android system applications are located in the packages directory. Look at all these folders. Each folder here represents one Android system application. For example, the settings folder contains the Android settings app that you use to configure your device. The launcher 3 folder contains the home screen launcher. The dialer folder contains the phone dialer application. The camera 2 folder contains the camera application. These are all system applications that come pre-installed with Android. Let's open one of these to see what is inside. Inside settings directory, you will see the complete source code for the settings app. You can see subdirectories like src, which contains the Java source code, and ras, which contains resources like layouts, images, and strings. There is also an Android manifest.xml file, just like any Android application. The important thing to understand here is that Android system apps are built the same way as regular Android apps. They use the same Android framework APIs. The only difference is that system apps come pre-installed with the operating system and they have access to some additional system level permissions. Now let's move to the next layer, which is the application framework. This is arguably the most important part of Android. The framework layer is located in the frameworks folder. The frameworks directory contains several subdirectories, but the most important one is the base directory. The base directory contains the core Android framework. Let me explain some important directories inside base directory. The core directory contains fundamental Android classes like context, intent, and bundle. The services directory contains Android system services. The API directory contains the Android API definitions. The packages directory contains the system UI components like the status bar and system dialogs. Now let me show you something very interesting. Let's navigate to the services directory. This directory contains the implementation of core Android system services. Look at all these Java files. Inside AM folder, you can see Activity Manager Service.java, which manages the lifecycle of Android activities. In Power folder, you can see Power Manager Service.java, which manages device power and wake logs. Inside PM directory, you can see Package Manager Service.java, which manages app installation and permissions. In WM directory, you can see Window Manager Service.java, which manages application windows. All of these services are started by one central process. Let's look at that process. This is SystemServer.java. SystemServer is the brain of Android. When Android boots after the Zygote process starts, SystemServer is the first major Java process that gets started. SystemServer is responsible for starting all core Android system services. If you look at the code, you will see methods like start bootstrap service, start core services, start other services. These methods start services like Activity Manager Service, Package Manager Service, Power Manager Service, and many others. Without System Server, Android cannot function. We will explore System Server in much more detail in a future episode dedicated to the Android boot process. Now let me show you something interesting. All those services we just saw in SystemServer.java are actually running right now on our Raspberry Pi Android device. We can see them using ADB. By using the command adb shell service list. Look at this output. These are all Android system services currently running on the device. You can see services like activity, package, power, window, and many others. Each of these services was started by System Server. This is the connection between the source code we just looked at and the actual running Android system. When you develop Android apps, you interact with these services through framework APIs. For example, when you call start activity in your Android app, behind the scenes your app is communicating with Activity Manager service through a mechanism called binder IPC. We will cover binder in detail in future episode. Now let's move on to the next layer, which is the native libraries layer. While the Android framework is written in Java and Kotlin, the native libraries are written in C and C++. These libraries handle low-level system operations that require high performance or direct hardware access. The native libraries are located in the system directory. The system core directory contains the fundamental native components of Android. Let me show you some important directories here. The init directory contains the init process, which is the first process started by the Linux kernel. The libutils directory contains common utility functions used throughout Android. The debugger D directory contains the crash handler for native processes. The toolbox directory contains basic command line utilities like ls, ps, and top. In logging directory, the liblog directory contains the Android logging library. All of these components are written in C or C++ for performance and low-level system access. For example, when your Android app writes a log message using log.d, that message goes through the liblog library, which is implemented in C++. These native libraries form the foundation on which the Java framework is built. Now let's talk about one of the most important architectural decisions in Android, which is the hardware abstraction layer or HAL. The HAL is what makes Android portable across different hardware devices. Think about it. Android runs on thousands of different devices, each with different cameras, different audio chips, different sensors, and different displays. How does Android handle all this hardware diversity? The answer is the hardware abstraction layer. The HAL provides a standard interface between the Android framework and device hardware. Hardware specific implementations are provided by device manufacturers, but the framework talks to all hardware through the same standard interface. Let's look at where the HAL lives in the source code. This directory contains the HAL interface definitions. Look at all these subdirectories. Each subdirectory represents a different hardware subsystem. For example, the camera directory defines the interface for camera hardware. The audio directory defines the interface for audio hardware. The sensors directory defines the interface for various sensors like accelerometer or gyroscope. The graphics directory defines the interface for GPU and display hardware. The Wi-Fi directory defines the interface for Wi-Fi hardware. These interfaces are defined using AIDL, which stands for Android Interface Definition Language. In earlier versions of Android, HAL interfaces were defined using HIDL or Hardware Interface Definition Language, but HIDL has been deprecated. Modern Android versions now use AIDL for defining HAL interfaces, which provides better performance and easier integration with the Android framework. When a device manufacturer wants to support Android on their hardware, they implement these HAL interfaces for their specific hardware chips. The Android framework does not need to know the details of the specific hardware. It just calls the standard HAL interface and the manufacturer's implementation handles the hardware specific details. This is what makes Android so flexible and portable. Finally, we reach the bottom layer of Android architecture, which is the Linux kernel. As we learned in the first episode, Android is built on top of the Linux kernel. The Linux kernel is responsible for process management, where creating and scheduling processes, memory management, where allocating and protecting memory, device drivers, where communicating with hardware devices, security, where enforcing permissions and isolating processes. The Linux kernel is the foundation of the entire Android system. The kernel directory contains the Linux kernel source code. Depending on your device, you may see different kernel versions. For our Raspberry Pi build, we are using a specific kernel version that supports the Raspberry Pi hardware. The kernel is written entirely in C and some assembly language. It is the lowest level of software that runs on the device, executing directly on the processor. Every Android app, every system service, every native library, all of them ultimately rely on the kernel to interact with hardware and manage system resources. When your app allocates memory, the kernel manages that memory. When your app reads a file, the kernel handles that file input output. When your app sends data over the network, the kernel manages the network stack. The kernel is absolutely critical to Android's operation, even though app developers rarely interact with it directly. Let's now summarize what we have learned today. We started with the Android architecture diagram, which is just a theoretical model. But today we mapped each layer of that architecture to its actual location in the AOSP source code. The applications layer is located in packages apps. This is where system apps like settings, launcher, and dialer are implemented. The application framework layer is located in frameworks base. This is where core Android services like Activity Manager Service, Package Manager Service are implemented. The native libraries layer is located in system core. This is where low-level C and C++ libraries handle fundamental system operations. The hardware abstraction layer is located in hardware interfaces. This is where standard interfaces for hardware components like camera and audio are defined. And the Linux kernel layer is located in kernel. This is the foundation that manages all hardware resources and system security. Now, when you hear someone talk about Android architecture, you will not just think about abstract diagrams. You will know exactly where each component lives in the source code. In the next episode, we will dive deeper into setting up the Android build environment. We will install all the necessary tools and dependencies needed to compile Android from source. After that, we will actually build Android from source code and flash it to the Raspberry Pi. By following this series step by step, you will not only understand how Android works internally, but you will also be able to modify the source code and build your own custom Android operating system. If you found this video helpful, please like and subscribe to Must Electronics to support this series.